hit the wrong button and I stopped it after about 5 minutes, but I posted a similar lecture from another class, from the pre-calculus one I do. So today we're going to first start off with a little bit of solving absolute value inequalities and equations. And then we're talking about what's transformations. So we're going to look at these, what did we call them? They call them toolkit graphs. So we've got the quadratic, which is a U-shaped, and cubics, and so we'll look at each of those different ones. But what we're doing is we're going to see from just having the graph of x squared, we actually can get every other quadratic is a transformation. It's a movement either horizontally, vertically, could be a reflection over the y or a reflection over the x, could be a stretch or a compression in either direction. So we'll look at how to make all those happen and the mathematics behind it. And that's basically the lesson for this week. So absolute values and moving graphs around by changing the formula a little bit. So let's go ahead and get into, well, actually, let me come back. I don't know if I introduced this, but I think I put an announcement. So what you'll start seeing is this weekly schedule will move. It'll be here for today and probably, let's see, this is Wednesday, and then Monday we will have a work day. So we're here at lesson 3 now. We'll do tutored math learning on Monday in lesson 4. So it's just kind of to follow along, and I'll keep moving it down the list as we make progress. Okay, so but that's and notice on the homeworks I will continue to move due dates so that it's open for you to continue working on it. It's best to try, like once we started lesson 3, try to get it either done or mostly done by next Wednesday so that you can jump into 4. It's okay to leave a little bit, so I'll keep moving the due dates till the midterm. And again, that's when you really want to have everything learned by then so that you can do well in the midterm. All right, so let's, this is what we're going to be talking about. Let me, still going, let's see, I need to get my tool, where is, okay, let me try something else. Actually, let's leave this open. Okay, that's what I need. Lesson 3, if you go to the learning objectives, you can get to the slide deck. There we go. Okay. So first of all, we'll start off with this is just kind of all the different types of inequalities you can have. this is what they call set builder notation. And the way we read this, the curly brace just tells us we're going to have a set. X just says X, and this bar here means such that. So it's X such that. This first one is that basically we read it X is between A and B. X is bigger than A but less than B, so it's in the middle. So X can either be in the middle, it can be larger than a number, it can be smaller than a number, it can be larger than or equal to a number. And notice this is just to emphasize it, when it's got the equal to, it becomes a square bracket rather than a parentheses, because that endpoint's actually included. And again, on both of them, if it has the equal to, we get the square bracket saying that B is included. Notice with the infinity or the negative infinity, we always have a parentheses, because you never really get to infinity. It's sort of this journey you're on that you keep going and going and going. It never ends. So these are all, again, just kind of maybe to come back and refer to. And basically what we're going to think of is if we are at a location, there's two things that can happen. Think about you're looking for a house, or a place to live. And you know the school you're going to go to. What do? Well, you say, here's my school or my work. I want to be no further than 5 miles away. So you draw sort of a circle around, and this is maybe 5 miles. I want to be within 5 miles of my school, my work, whatever. Okay, so that's one thing that happens. The other thing that could happen, I'll do it up here, it's a little easier to see, is you've got something like a paper mill, which I used to live fairly close to when I was in Oregon. Actually, it was in Albany. It was 14 miles away, but when the wind changed, you knew you were, I don't know if you know about paper mills, but they have a distinctive smell that is not real pleasant. And so in that case, you might be wanting to hear, let me live anywhere, I want to be at least 5 miles away or something like that. So it would look like this. I could live 20 miles away and I'd be happy, but I want to be at least 5 miles away. So those are basically the two types of problems we're going to face. We're either wanting to be close to something, so that is between our two boundaries, or we want to, those boundaries, we want to be further away from those two. And we'll look what that looks like mathematically. Okay. So we'll just look at some examples. So this one, greater than. So this is saying whatever this is, x is supposed to be greater than 5. So the way we're kind of thinking is, if we'll see if it works out that way, but that x has to be a number that's more than 5 away from something. And the way we can solve it is we leave this inequality. As long as we do the same thing to both sides, we keep that, whatever that inequality is, we keep it the same, because we've done the same to both sides. So one side right now, this left side is bigger, that's what it, and this is smaller in comparison to each other. So what we can do is we can, again, for solving for x, like we were doing before, I believe, we just do the same thing to both sides. So that gives us negative 2x. The same, the symbol's the same, and now it's 6. And then what do we need to do to get x by itself? Divide by negative 2. Is there anything else we need to do as we go through this?
Do you flip the sign?
Do we? Good question. Let's look at, do we need to change the direction of the sign because we divided by a negative? What if we had 4 and 6? Which of those numbers is bigger?
6.
6 is bigger, so we could go like that. And we could use the equal to as well, but we know they're not equal. We just, so, but look what happens if we divide both sides by negative 2. 4 divided by negative 2 is negative 2. 6 divided by negative 2 is negative 3. Which number now is actually bigger? Negative 2. So notice how that, because it was a negative, it actually changed the order on us. -2 is bigger, so we have to go so we have to flip the symbol. But sometimes you just memorize that, and sometimes you'll get it wrong. But if you remember, you can always go back and check the relationship of an inequality by putting two numbers that you know. I just chose 4 and 6. You could have done any two numbers, and then multiply or divide by a negative, and you'll see that the relationship changes. We do. But the problem is here we have it as variable, so it's not as clear. Yes.
That would apply to like multiplication as well.
Exactly. It's either multiplication or division. It didn't apply when we were if we were going to subtract one from both sides, or that's okay. Subtraction, addition. But when we multiply, not just always when we multiply or divide by a negative number, that will switch the order. Had we done it by +2, right, I'll just do this, 4 and 6, divide by +2, then we have 2 and 3, and it's still 3, the right side is bigger than the left. It did not change. But the problem is over here with the variable, it's not real clear that that's what's actually happening when we divide by a negative. We are changing the direction of which one's bigger and which one's smaller. And so we end up over here with -3, and over here with just x. Yes?
Is there ever a case when you're multiplying or dividing by a negative that you don't flip the sign?
So maybe with zeros there, but I think you always do. Yeah.
Okay.
I'm trying to think that there might be one weird example, but in just about every case, because that process of multiplying or dividing by a negative will change that direction.
Okay.
I think even with 0. Okay, and then what we do is, okay, what are we going to do? This is saying we can use a number line to kind of graph it out. -3 is what we're talking about. -3 is included, so we'll put a solid dot, and x is smaller than -3, so smaller is to the left, rather, so x is living over here, so it would be everything this way to -infinity. There's a positive infinity over here, but this side's not included. So for our solution, it's not just a number, it's not just -3, it's a whole interval. We're going to go from -infinity to -3. -3.
Squiggle line, is the squiggle everything that's included in it?
Yeah,
Okay.
yeah. Maybe I should do something like this and just, okay, we'll shade it in. But yeah, we're including all of this, and we keep going. This side over here is not included. Okay. And so we'll use a bracket for the because -3 is included, and we're good. So far so good on inequalities. So we treat them just as if it was sort of an equal as we go solving them. The only thing that's different, when it's equal, we can divide both by negative. It doesn't really change the equal, but it does change which side is bigger. So we always have to remember to flip that inequality, multiplying or dividing by a negative. Good.
What was on the parentheses on the -infinity side? How did you determine that? Because I understand the bracket side.
Okay, because it's included. We use a parentheses wherever the endpoint is not included, and the idea with infinity is you can't ever get there.
That's what I was thinking.
Yeah, good. Although maybe you believe you can get there, you could use a bracket. And I'd like to get there someday, right? Then you can stop going. Okay, so we'll do a few, and I think I did pare this down a little bit, so we'll try to get rid of some of the, so again, solving, we add 2 to both sides. 3x is less than 3. Divide by 3. Do we need to change the direction of the sign?
It's not negative.
Excellent. So then it's just x is still less than +3. And again, just to kind of get a view, here's +3. X is smaller, which means it's to the left. It's over here. So we'll shade this way. It's going this way. And again, there's negative infinity on this side, there's positive infinity on that side, but it's just our solution. And when I do this, I can say it's just going to be from there. And on the 3 this time I use a parentheses, right? Because there is no equals to. 3 is not actually included. 3 is not less than 3, it's equal to 3. So 3 is not part of our solution. We've got an example here with an x on both sides. Yes?
For the first one, how is 3 divided by 3 3?
I make things up as I go. It should be 1, shouldn't it? Okay. Thanks for catching me. Sometimes, because I record these and I put these out there, and sometimes they don't get record, and they're going, "Didn't you know that 3 divided by 3 is 1?" Again, sometimes it just. Thank you. That's why I have this eraser. But see, that's why I don't put too many points, because it's easy to fix. It's 1, and so 1's. There we go.
I'm glad you noticed. I would have looked back at my notes later.
I know, that's, and sometimes people say this, I go, yeah, of course. And so you wrote this, I go, I did. Well, and sometimes it was like a 2, and on one of my videos, I wrote a 9. You know, I don't even know where the 9 came from, and they're going, how'd you get 9? I said, I made it up. I don't know. It's the thinking process. Thank you so much. Okay, and I wish I could get rid of the screen somehow, but so just holler out. So let's take a look at this one. When we have an x on both sides, since we want to solve for x, right, we want to get x and its relationship either bigger or smaller than a number. What should we kind of do first since we've got x's on both sides?
You can subtract 2x.
There we go. Let's bring them together. I always, let's get the family together, because they're like terms, right? So we could subtract the 2x. Could we have subtracted the 4x? We could have, but then that gives us a negative, and then we'd have to remember to flip the sign. And so it's easier if we work to try to keep things positive, just like life. Try to keep it positive if you can. It just will make, so 4x minus 2x is going to be 2x plus 7. This becomes 0, and that leaves us with negative 3. So now it's a little bit more manageable, right? And then we just do like kind of we did before. We'll subtract 7 from both sides. And we get that 2x is greater than or equal to negative 10. And again, we haven't changed the direction because we don't need to. And then we divide by positive 2. And so that's going to give us x is greater than or equal to negative 5. Okay. And again, I just used a little number line. Here's my negative 5. Positive infinity there, negative infinity there. X has to be, in this case, bigger than negative 5, so that means to the right. So x lives over there. So we're going to shade, oops, I want to choose that one. I want to shade this direction as what's negative 5. Is it included? Yes, it is, because of the equal sign. So we're going to get a bracket here to infinity with a bracket there. So notice it's the other side. You don't have to draw the line graph, but I find it's easy. It makes sure I get everything lined up correctly. But if you're okay and you're able to write down the interval, it's not required, but if you're having problems like me, I get them in the wrong order. This helps. Question.
And then you did flip the signs because why again?
So in this case, we're dividing by a positive number. So when we divide by positive numbers, it doesn't change anything. The bigger side stays bigger and the smaller side stays smaller.
Okay, so when you're trying to solve for x, if you're dividing it and it's a positive, you don't have to flip it. But if it's a negative, then you'll need to.
Yes.
Okay.
And it's just because that negative changes direction.
So if we did in the beginning and you subtracted the 4x, moved it over, would you still get the same answer?
You would still get the same answer, but then the x would be on the other side. And so that's why you'd have to, at some point, flip the symbol to get it going in the right direction.
And plus
Good.
it's just more work then.
Right, and that's why, so it's smart to try to keep, if you keep things on a positive, it saves you a step. And then you don't have to forget, Good, good. Good questions. Anything? Okay, good. The reason I put this here, so there's this fraction thing here, right? Who likes fractions? Nobody likes fractions. Even the math teacher doesn't like fractions. I like decimals. That's why I like it. So, but what I'm going to show you is this. It's called clearing fractions. When I was at Oregon State, a number of my students called it killing fractions because they hated fractions so much. But we can get rid of all these fractions by doing one thing. What is the one thing we need to do? We will multiply both sides by what? A common denominator. So we're not trying to get a common denominator, but if we multiply, so what we've got a denominator of 6, one of 4, and one of 3. So what number? 12. Because 4 times 3 is 12. 6 goes into 12 as well. We could do 24 if you wanted. You could multiply them all together, so you can get as big as you want, but if you get the smallest one, it sometimes might save you something. So what we're going to do is the common, I just say a common denominator. It doesn't have to be the lowest, but lowest will help, is going to be 12. So we're going to multiply everything by 12. So let me rewrite it down here just so it 5x less than or equal to 3/4 plus 8/3 x. And so we're going to go ahead and we're going to multiply this side by 12. And think of it as 12 over 1. That 12 is up in the numerator. And then we're going to multiply this side also by 12 up in the numerator. Okay, yes?
Why wouldn't you just change all the denominators to 12 and then multiply the numerator?
You could. That's sort of what we've learned with when we were working with fractions. We'd get the common denominator and then work with the fractions. But you're going to see if we take that common denominator and multiply, we will actually get rid of the fractions. Okay. And then it'll simplify the process from there. Right. But right, that's some of the stuff is we were taught the wrong way to do most of our math because in elementary school they wanted us to work with fractions, so they taught us how we could keep working with fractions. Well, they should have told us how to get rid of the fractions, and then we'd have an easier life from there. But so what we can do with this is, it's really 12 times 5, but right, we could take 12 and divide it by 6 first. So on this side, I'm going to take 12 divided by 6. 12 divided by 6 is 2. Notice that's up in the numerator. And then I'm going to get 2 times negative 5, which will give us negative 10x. So far, so good? Okay. Over on this side, we're going to have to distribute this 12 to both of these terms. So I'm going to write it in here. If I multiply this one by 12 over 1. Again, we were taught to multiply the tops and multiply the bottoms, but if you do the division part first, you actually save yourself some work, because otherwise 3 times 12 is what? 36, and then 4 divided by 36 is 9. Well, watch. 4 goes into 12 3 times. 3 times 3 is 9. Isn't that easier to think through? I think so. So why get a big number and then have to figure out how to work with it? Keep our numbers small, try to keep them smaller, and they'll just be easier for us to work with. Okay. Now notice we multiplied by positive 12, so at this time I'll say we bring down the symbol, it doesn't flip. But over here, this 3/4 is now going to become 3 times 3, which is 9. Notice the fraction is gone. We killed the fraction. Okay. The thing you have to remember is then we also have to distribute here, so we get 12 over 1. Again, you could take 12 times 8 and get a big number and then divide it by 3, or you could just say, let me take 3 into 12, which is going to reduce it. That's going to be 4. Now 4 times 8 is 32. Plus comes down. And now these are equivalent. Ones without the fractions. They're bigger numbers, right? But because we multiplied both sides by the same thing, we made them both 12 times bigger, but the relationships are the same. Okay, so it's one little trick. It's kind of out there, and it's not what we were taught to do, but you'll find that this comes into play as we go forward. It'll make working through some of your solutions a lot easier.
What are, like, aside from, like, the only thing I can think of is baking, like, what are, like, practical applications for fractions?
When you need a part of things, so like in engineering, if you've got two machines working together, each is doing a portion of the job, there's a fraction involved. I like to think a decimal is a type of a fraction, right? 0.2 is actually 2/10, but it's written as 0.2, and it's so much easier to work with. So
Gear ratios too.
there. Okay, thank you. Gear rate.
2 to 4, stuff like that.
Exactly. So when we're doing these things, anytime we're talking slope, rates of change, that's going to give us a fraction. So sometimes that kind of fractional thinking is helpful, but not all, sometimes it's hard. Yeah. So anyway, we're not done yet, though. We just got it to a place where we cleared the fractions. Now what should we do? What's that?
Oh, no.
Oh. So solve for x. Again, we've got x's on both sides, so what should we do? Get them to one side. Which one do you want to deal with?
Can we move the 9 over and then move the 10 over so it's a positive x?
Well, you could, but if you move the 9 over, notice it's not a 9x. It'll just be 9. So there are multiple steps, but you were suggesting to try to keep it positive. So if we add 10 to both sides, here's the thing, though, that happens when we do this. When I take negative 10 plus 10, what happens?
You just get x.
You get nothing.
You get nothing. So do I just leave that blank?
Put a 0.
Put a 0. Yeah, placeholder. It's actually 0. I have 10 x's. I'm going to take away 10 x's. Think of it that way. The x is actually even gone. I'm left with 0. So that's where the problem comes in. Is some people will say they'll leave it blank, or they'll put 1, or they'll put x, but it's canceled, but it cancels out to 0. Okay. And then we get 9. What's that? 42x. And then now I would subtract the 9. And sometimes that's why maybe if it feels better, subtract the 9 first, so there's something over there, so you don't end up with 0. But and again, we're going to subtract 9. That's okay. We don't change the symbol, and then we get 42x. And then what's the last thing to do here? Divide by 42. And so we're going to get x is less than or equal to 9/42, but 40, they can both be divided by 3. I know 3 goes into 9 3 times, because 4 plus 2 is 6. 6 is divisible by 3.
I got 3/14.
3/14. Good. So take 42 divided by 3, you should get 14. Thank you, because I didn't know what it would be. I'd have to do some work. And it's negative, right? So negative 3/14. Could have left it as 9/42. Could have written as a decimal. Again, sometimes these things are not going to make nice decimals, but that's our answer. And again, x is bigger than this. So you could do the number line, or you could say, well, x is bigger than that. That means x is going to go off to infinity. So negative 3/14 is the smallest we could be. It's equal. And this is our interval notation. Again, you could lay it out on the number line too, but as you go through these, you might start to pick up just, okay, that's my answer, so here it is. Is that so far so good? Any questions? All right. Now we're going to talk about compound inequalities, and then we'll get into something, what happens with absolute values. And that's really where the distance thing comes in. So compound is, and this breaking over the line, so compound is like 4 is less than x is less than or equal to 6. This is really two statements. It's the two statements that 4 is less than x, or x, yeah, 4 is less than x, and x is less than or equal to 6. But we can write it as one inequality. So you could do it either way, but if they give you a compound what's called a compound inequality, and again it works well if x is between these two numbers, then we'll see how we would go about solving an equation that might involve a compound like this one. The other kind of a compound, let me back up. So this, when we have the and, how can you be this and this at the same time? What this is saying, if we were to put it on a number line, here's your 4, here's your 6. So to be both of them, you are between those two. So at the same time, you're bigger than 4, but you're less than 6, right? This is the only way it happens. The other thing that could happen is the or. And notice as we go to solve these, what we're going to find with the or is there's some left point and a right point. I'll call this left and this right. And what's going to happen is you're bigger than the right. I said R, not. And you're less than the left side. So that's what's going to happen with this when we have an or. And it's still a compound because it's saying that both of these things have to happen. They can't happen at the same time. You're either on this side of town or you're on that side of town, but you're so many miles away from something. So we'll go ahead and actually solve this one. And it's really, when you have the or, typically we're working through two different ones. So we take, let's back up. 3x minus 8 is less than negative 11. And then we'll just put out over here 5x plus 1 is greater than or equal to 6. Okay, so x plus 1. There we go. So we just really have two problems to solve. So on the left, we'll add 8 to both sides, giving us 3x plus 8 minus 8 is 0, so that's gone. And negative 11 plus 8 gives us negative 3. And then we divide both sides by 3. And watch, this time I'll get it right. 3 divided by 3 is 1. It's not 3. Okay, so that's our x. And this becomes negative 1. Okay. So far, if we were to draw a graph, we got negative infinity over here, positive infinity over here. I'll put my negative 1 here. We know negative 1 is not included, but x has to be smaller than that, so it's going this way. So that's one part of the solution. I come to solve the other part of the compound inequality, and for this one, I subtract 1 from both sides. So I've got 5x greater than or equal to 5. Divide both sides by 5. That becomes 1. X is greater than or equal to positive 1. So the other point I have here is positive 1. That one is included because of the equals to, right? So that's included. X is bigger than 1, so that means it lives to the right. So it's going to go this way. And again, right from the number line, I could say, well, okay, that one is included, so it'll have a bracket, go to infinity, parentheses. This side, go from negative infinity to negative 1. Negative 1 is not included, so I'll put a parentheses. What goes between these two? The U for union. So that's kind of the open space in between. So we can kind of see it visually with the line. This is the answer they're going to look for using interval notation or interval form, I think they call it. So we see that. So compound inequalities. Ors will always have that union in between because it's going to be the two sides. Ands is always continuous, so we just have that one thing. Okay. The thing when we have a compound inequality, and remember this is really the and, the x is in the middle, sort of a cool thing you can do, you could split it into two different inequalities, right? But you could also just work it all at one time. So whatever you do it's basically we've got three sides. So what I do is I kind of, right, I'm going to separate out here. I've got three sides. I'm going to solve for x in the middle, but whatever I do to the middle, I'm going to do to all three. I guess not sides are to the left, all three portions. So what I would do is I would add 8. So if I add 8 there, I add it here, and I add it here. So we can just work with this compound inequality, work with all the portions. 4 plus 8 is 12. I still have the less than part here. 2x minus 8 plus 8, so that cancels. We just have 2x left. And then we have this inequality less than or equal to 18. Now what do? Divide everything by 2. Divide everything by 2. Do we need to switch the symbols or anything? No, because that's a positive. And we get our final answer. 12 divided by 2 is 6, which is less than x, which is less than or equal to 9. And again, if we see that when we graph this, we've got 2 points. We've got 6, which is not included. We've got 9, which is included. And x lives in between the two. Let's go with green. So it's going to be this space in between. And now that we've got it, so there's a parentheses on the 6, a comma, and a bracket on the 9. Interval notation. And that's what the number line will help you get things in the right order.
So it's like the same as if you had like whatever equals whatever, but just more.
Yes.
I don't know if that makes sense.
Yeah, it does. It's more than one solution. When we have equals, we're going to get one number, right? When we have an inequality, we get we get an interval where any of these numbers will work. So it's kind of like you go to apply for a job. You say, I want $12, but I said, no, we're not going to pay you 12, we'll pay you 15. Oh, okay. So really you're asking for an equality. You would like to get more. You won't get less, right? Probably not. Well, sometimes we ask for more. But anyway, that's sort of the idea. A lot of things in life are really inequalities. They're not just, this is what I need to get. I want to get 15.55 per hour and nothing more, nothing less. No, I'd like to get more. But I'll accept this is sort of a minimum. So a lot of problems in life are really inequalities. I've got $100 in my pocket. I could go, so I can spend up to $100. I can't spend more than that, but I don't have, doesn't mean I have to buy something for $100. Okay. All right. We're going to skip over this one. So I wanted to get into absolute value. So what does absolute value mean? The focus is on, it's really the value of the number without the sign, okay, regardless of whether, so in a way of thinking, if it's a negative number, so absolute value of -3, we say it's got the value of 3. It's a value of 3. Negative kind of tells us the direction. So absolute value is giving it to us without direction. Absolute value of positive 3 is still positive 3. So it's always going to give us a positive value. Okay. The thing is notice inside this absolute value, the positive value gives us the same answer as the negative value. So what happens here is when we go to solve for an inequality, we have to take the inside part. That could be either positive or negative, right? And whatever this relationship is. So it's really going to involve a compound inequality. So we get 2x plus 7, and I'm just going to take the positive side, less than 13. Okay. The other thing that happens is this inside could be negative 13. And what's going to happen here? Is it going to be less than, or is it going to be greater than? Thank you. So the symbol's going to flip because of that negative. So with the absolute value, we're going to get one side that's positive. It's going to be just as it is. We're going to get one side that's related to the negative, but it's going to flip it. Good. That's the big, let's see, make sure I do it. So the symbol changes direction on the negative one. So we're comparing to 13, sort of the boundary. So we solve for where it's equal, or sort of as just statement, in this case, less than 13. And then the other one, we'll flip the symbol and get that relationship to negative 13. Now some of these are ands and some of them are ors, and I can't ever remember which one until I get done. So that's why now we go, again, we solve each one individually. So this will start with this side, subtract 7. And we get 2x less than, what's that? That's 6, positive 6. And then we can divide both sides by 2, still keeping everything positive, no signs changing. X is going to be less than 3. So that's one of the answers. Over here, we'll do the same thing. We're going to subtract 7, but notice we're doing it from negative 13. So we get 2x is greater than negative 20.
Yeah.
And then divide both sides by 2. So we get that x is greater than negative 10. This is where I find doing the number line really helpful, because you know which one's where. It helps you get things lined up. And I'll just do it up here. So I know I've got positive 3, that would be about here. It's infinity over here, negative infinity. Negative 10, okay, that's to the left. Here's my negative 10. And then now I've got to sort of highlight x is less than 3, so it means it's to the right of 3. Got to go this way. I'm not going to go all the way, but I'll stop there. And then this other one, x is greater than negative 10. That means it's to the right. Oh, it's one of these where I get the middle part. Okay. And I could have gone out the other way, just depends on which one it was. I wasn't sure.
And then they're both not included because it's not 4 equals 2.
Very good. Exactly. So this is just strictly a strict inequality. So they're open circles, and so we could do a parentheses and a parentheses. So our answer is negative 10 to 3. So that's our interval. X can be any of those values, and the inequality holds. Yes, sir.
When you're solving it in absolute value, you have to do positive and negative?
Yes. Because remember, that's what that absolute value means. There's actually two numbers that you can get. Positive 3 will give you 3, negative 3 will give you 3. So there's a value for x that will give us a positive 13. That comes out. There's a value for x that will give us a negative 13. That also would satisfy. And again, there's more than one solution. It's all those things in between. Because whatever any of these x values, like plug in 0, will get a value that is less than 13. Plug in negative 9, Negative 9 is negative 18, you get negative 11, but take the absolute value of negative 11, you're still less than positive 13. So all of these numbers will work. But yes, always just remember absolute value, you're going to get two. One positive, one negative. And on the negative one, you always have to remember to do what? Flip the sign. Yeah, and when you multiply and divide. So it's just those all kind of go together. If you can just remember, it's just all. But be careful. I've had some students say whenever a negative's involved, you flip it. But then when they're subtracting, they want to flip it, and that's it's only multiply, division, or inequality. So this will be the other type. Notice it's greater than. What we're going to do is this. We want to be far away from the paper mill. But again, to set this up, we do exactly the same thing. So we do 3x minus 1 is greater than 11. So that's the positive version. Just write it down. To get the negative version, we do 3x minus 1. Its relationship to negative infinity. What way does the symbol go? The other way. We flip it. And then now we solve each one, put it on the number line, and we'll get our inequality. So again, add 1 to both sides. 3x greater than 12. Divide by 3. X is going to be greater than 4. On this side, we add 1. We get 3x is less than negative 10. And when we divide, 10 divided by 3 is still negative 10/3. Doesn't go in evenly, doesn't reduce. And so again, we come here, got negative infinity at the left, positive infinity on the right. Sometimes I'll throw a 0 in there to just get my reference points. We've got something where relationship with 4, so there's positive 4 on that side. Negative 10/3, not exactly sure where that is. It's a little bit bigger than negative 3, but I just have to, we'll put it somewhere over here. And then what I've got is x has to be bigger than 4, not including 4, but that means x lives over here. So it's going to go that way. This one's saying x is less than negative 10, so it lives to the left, so it lives over here. And so I've got to shade this way. And again, the endpoints are not included. And usually you'll find either both included or both not, depending, because they come from the inequality, right? And so what do we get? We get this as our interval. We get a union in between them. And so see, by putting it on the number line, you kind of get your answer. You could then rewrite it, negative infinity to negative 10/3, union 4 to infinity. Okay. So that's the other one. So whenever you have a greater than, an inequality, or an absolute value with greater than, you get the outside, you're trying to get away from something. When it's a less than, you'll get the middle part.
How come on the last problem we didn't do it as a union?
Because we started with a less than, and notice it was it's continuous. It's everything in between.
Gotcha, because then there's no infinity. It doesn't need to be a union between.
Yes.
Okay.
And so this one, and again, I have a hard time remembering until I get to this point. This is really the and.
Okay.
We can be both, and this one is actually an or, because you can't be both places at the same time, but you could either be left side, the west side of town, or the east side of town, type of thing. Good question. Good. All right. So yes. Oh, okay. That's fine. That's fine. Just didn't want to miss out. Okay. So now, does anyone need a break? Take a deep breath. Okay, that's our break. Now, And if you do need a break at any time, just head out. We go till what, 12:20?
Yeah.
So yeah, I think we'll probably be done in about 15 or 20 minutes. We might even be done in 5 minutes because I've got a little thing I'm going to show you that will kind of basically put everything together, and then we'll go through the slides and see how that works. So I'm going to, and again, if everyone really wants a break, just let me know, but I find if we just kind of keep moving, we'll get done early, and then we'll take the break at the end by being able to head out. Okay, let's come here. We're going to keep everything so far. I'm going to go, this is still here. Okay, so I've got a Desmo set up. I think I can save this so that you could play with it if you want. Notice the function that is graphed. Let me take this off. The function we have is x squared. This is just x squared. So this is one of our toolkit graphs. And what we're going to see is we can change this, and we'll see that it works for all of them. Below it, I have that function, so it's f of x, and notice there's a number multiplying on the, well, let me just, with the function f of x, there is an outside of the function, outside of the parentheses. So this letter a, which is multiplying, is outside. This plus v is outside the parentheses, right? And then there's inside the function, which is inside the parentheses. So this little a2 that's multiplying by the x, that's actually inside the function. And the h, plus h, is actually inside the function. Does that make sense? Kind of. Well, let me show you something. Let me turn this on. And right now I have a and a1 set to 1. So when we multiply by 1, do we change anything? No. So that's why the blue parabola looks exactly like the red parabola. If we add 0, if we add 0, do we change anything? No. What's going to happen, let's go with maybe the obvious. What if, so on the outside of the function, right? What happens with the function, I plug something in and I get a y value. What if I add a number to each of those y values? What is that going to do to the graph?
Move it up or down.
Move it up or down. So let's see what happens. So that's the v, and watch, v is currently 0. Watch as I change v. If I move it in the positive direction, whoa, it's moving up. So 3.4, it's moved up by 3.4. If I have a negative, it moves it down. And that seems right, because if I take a y value and I subtract a number from all of them, all the y values become smaller, so the graph has actually gone down. So that's our first thing, is on the outside, if we add or subtract, we move it either up or down. We okay with that? Again, we'll go through some slides that kind of show those, but I just wanted you to see that you can actually, that's exactly what you see happening, right? It moves up and down. And you get, this sort of animates it. So let me put it back at 0. What if inside the function we add or subtract a number? What do you think is going to happen then? So outside the function moved it up and down. Inside the function is going to affect the x. What does the x determine? Left or right. So that's all that's happening. Is, have you ever, do they still have those little red boxes? It's called an Etch-a-Sketch with the little knobs that you can, used to play with those as kids, right? You know, and all it is, if you ever take one of those apart, all it's got inside is these two little things, and one knob moves it left and right, one moves it up and down. That's all it's doing. We control everything by controlling left and right. So let's see what happens with the h. If I move the h, if I add something to x, what do you think is going to happen to the graph? Which way will it move?
To the right.
To the right. Whoa, it's moving to the left. And this is the first thing that happens is, yeah, you thought it would go in the positive direction, but when we're inside the function, think about when you look in a mirror. What happens in a mirror? It turns everything opposite. You're playing with your right ear, but in the mirror it looks like you're playing with your left ear. So we're inside the looking glass. Everything happens opposite. If I subtract, I actually move it to the right. If I add, I move it to the left. So I think when I'm adding, I move it in the negative direction. When I'm subtracting, I move it in the positive direction. Just remember, everything that happens inside happens sort of in a reverse. Okay, but you can see that, yes, it's going to change it, but it just goes in the opposite direction. Outside the function is what you see is what you get, right? Add, you go up, subtract, you go down.
So if you have this x squared, if it was like x squared like plus 2 would move it up 2.
Mm-hmm.
But if it was x plus 2 squared, it would move left?
Yes, in the opposite direction. So for inside the, and then we'll go through some slides that show what's actually happening, what's inside the function, what that looks like. But that's exactly what would happen. Yeah, it's exactly what happened. Now, what about if we multiply? And again, this is, so we can move it up, we can move it down, right? We can move it left, we can move it right. What do you think multiplication will do? Let's take on the outside. Anything outside the function will affect the y. If I multiply every y value, say by 2, what's that going to do to every y value? It's going to stretch it, isn't it? So let me, A is our, so this is going to affect the y. Does that look like it's sort of stretching it upwards? And that's exactly what's happening. So every y value is now 3.5 times bigger. And again, the bigger you do it, notice 0 didn't change, because when you multiply any 0 by anything, it stays where it's at. But everything else just kind of got pulled up straight. And if I multiply it by a number between 1 and 0, notice it becomes wider. Okay, so it's kind of compressing it, is what we want to think. And I can compress it down. What happens if I were to multiply by 0? It's a straight line at 0. So, right, because that's what happens. Everything is 0. It's the 0 function. It's y equals 0. What if I multiply by a negative? It'll also be a reflection. So that's the other thing we see, is that it goes the other way. It reflects it over the x-axis. So negatives do the same thing. Okay, but anything that's multiplying on the outside will be either a vertical stretch or compression. And if we do it with a negative, it actually will flip it over the x-axis. It's affecting the y, but it flips over the x. And again, we've got some slides that will take us step by step. Just kind of, we see it happening, right? So we'll take this back to 1, so that it's, again, we're multiplying by 1. There we go. Whoops. Now, what if we multiply inside the function? It's going to affect it horizontally, right? So if I multiply by a number bigger than 1, will it stretch it or will it compress it? Good. The opposite of what you think is going to happen, remember? So now this is my A2, which is inside the function. Isn't that look like it's getting squished? It is getting compressed as x gets bigger. Of course, it's hard to tell the difference between a horizontal compression and a vertical stretch. They both look the same on this particular function, and so then if I multiply by a number between 0 and 1, we're stretching actually, right? You can see horizontally it's getting stretched. And then if I multiply by a negative, what's going to happen? What happened when we did by a negative before? It reflected over the y. But since we're affecting the x, which one's it going to reflect over? It's actually going to reflect over the y-axis. but you can't tell the difference because the positive comes to the negative. So in this case, we don't really see it, but that's actually a reflection over the y-axis. Okay, so we'll look at some that you can tell the difference. Okay, and again, all that happens. And what I want to show you here is we can put in any of the toolkit functions. Oops. Get back to there. We could put in x to the third, not 23rd, x to the third. And we could see how that happens. Again, if we move the vertical, we can move it up or down. Same thing. We can move it left or right, but again, positives move it to the left, negatives move it to the right. And then we can also do a stretch or a compression or a reflection as well. Okay, so we're going to kind of walk through these, but those are really the three things we're going to talk about. Translation, which is moving it left or right, up or down, and so forth. And I'll save this somehow and I'll put a link to it. Let me log in here. See if it'll let me. Well, maybe I'll do that later. So we'll come back to here. Okay. So this is just kind of going to talk through what we did in more words. So this is if we add a number, they use K. I use V for vertical. So if we're adding K, or K could be negative, right? It's going to give us that vertical shift. So notice it's outside of the function. It's outside of the parentheses. If K is negative, the graph will shift down. Positive, it shifts up. Yes?
So, like, would the parentheses always be written?
Not necessarily. So, like if they give us a function y equals 2x squared plus 4x, and then they say they want us to move up, let's move it up 3. Well, what are we going to need to do? We would need to add 3 out here. So we would see it, this is the function they gave us, so we could add the parentheses, but they might not always have them there. Okay, so if we're given a function, if this is what we're starting with, we'll start with that, put the parentheses around it. And then, so we're doing it on the outside. Does that help? Yeah, because it's, you'll see as we get in there. The inside of the function is where we put stuff in, so it's always going to be inside the x. So we kind of think that's really the inside part of this function. You have 2 inside places. To do a horizontal shift, you've got to go into the x and then subtract, add or subtract. Now this is why they do the opposite. So if h is positive, they have the negative here. It actually moves it in that direction. If h is negative, it moves it in the other direction. Okay. So that's going to give us, again, whenever we're inside the function, we'll be shifting it horizontally. Yes?
So if they don't give you parentheses, how do you know if it's like x minus h or like x minus h?
When they use this notation, they will have the parentheses. And so again, let's take our function. If they gave us something like y equals 2x squared plus 4x, they're going to tell us that they want a horizontal translation by, say, 3. Let's move it. Let's move it to the right 3. So we know to move it to the right, that's in the positive direction, we're going to need to actually subtract 3, right? So while they don't have the parentheses, we know it has to happen inside the function. The inside the function is wherever there's an x. So what we're going to want to do here is f of x plus 3. So we're going to rewrite that as 2 x plus 3. Wait, did I say that? We want to move it to the right, x minus 3, sorry. It's the opposite. So wherever there's an x, it becomes x minus 3. So that's how we do it. Again, it wasn't set up with these parentheses, but since we know we want to do a horizontal shift, it has to be in there. We have to know to add those. If they want something on the outside, again, we sort of impose the bigger parentheses and we do it outside the function. That's the challenging part, though. You hit on the challenging part of when do we put parentheses and when are we inside, when are we outside. So what they're going to do, so this one is an example, adding a constant to a function. So this is g of x. So they're giving us the function f of x. And if I've got this new function that is f of x minus 2, what does that look like? It's the same function. Everything gets moved down 2. So 1, 2, 1, 2. So I move every point down 2 and then kind of connect them. And maybe this one, 1, 2 would be something like that. 1, 2. And, I would try to, and again, my artisticness is sort of there, but in the homework, I think they give you some graphs that you can do that with, and they give you better tools where you can just basically move them around. This one, what are we doing? X minus 2 is inside the function. What's that going to do to this graph? Move it to the right, so everything goes this way. So the y values stay the same, but the x's all shift by 2. So this comes over 2. This comes over 2. I got that one. This one comes over 2. This one comes over 2. And then I try to sort of connect them, and I think that looked kind of like what happened. It's kind of, but just that's the idea. Yes?
So if it was a plus 2, it would be 2 to the left.
You got it. So just remember, the inside is always, it's like looking in the mirror. It's the opposite of what you feel is going to happen. The outside, if we're outside the function, up or down, is going to be what our intuition tells us. Okay. We'll look at this as a table. So on a table of values, we're going to create a new, so notice we've got this f function. What's happening here if the new function is the old function plus 3 on the outside? What are we adding 3 to? Which number?
The fx, the y value?
The f of x or the y value. So yes, so we're going to add 3 to each of these. The x's are not changing, the y's are changing. So we're going to get 4, 6, 10, and 14. So those are that. So those would be the shifted function. I guess I could cross those out. This is now g of x. Okay, so that's what it looks like on a table. We're changing the y values. Okay, maybe I should do a new table over here, but we'll do that with this one. For the second one, they're also using g of x, but what's happening to this?
To the x values?
Changing the x values. So notice actually what we'll do, and we're adding 3, so it's supposed to move it which way? To the left. So we're actually, yeah, so if we were to graph this, we would want this point to move to the left 3. So we're actually going to do the opposite operation. So 2 minus 3 is negative 1. 4 minus 3 is positive 1. 6 minus 3 is positive 3. And 8 minus 3 is positive 5. Nothing happened to the y values. They're still 1, 3, 7, and 11. But if you were to graph these two things, you would see that the new graph has shifted to the left 3. Does that make sense? Yes.
So when it's inside the function, you're doing like everything is opposite. You're doing like the opposite
Operation.
plus or minus.
Yes.
Yeah.
To make it all happen. Yes.
Why is it like that?
I really don't know. No. What I visualize is what's happening is with the input, since that happens first, you're basically moving the axis 3 this way, which when you do that, so 2, if you move the axis over 3, the point has not changed, but now it's, instead of being at 2, it's at negative 1. So that's the only thing that makes sense with me, but why is that? I don't know. It's just because it's happening really inside the function at the creation of the function. When we're doing outside the function, everything's already happened and it's an add-on. So the vertical, you get what you think. But that's the best thing I can say is just as you work through these, you'll kind of get a little bit better feel for it, and you'll just see that's what needed to happen to make it work, and it just does. Just is because it is. Some things are kind of like that way. It's a part of nature. Okay, so then there's these ones, and again, you could also go into like the Desmos program and do this, but what we do is we think of what is our toolbox function. So what does the square root of x look like? It looks something like this, and I'm not real accurate on the numbers. I know that 1, 2, 3, 4 should be 2. I'm pretty close. And so the transformation f, again, on the inside x plus 2, what would that look like? Do I go to the left or the right? Go to the left in the negative direction, 2. And so I would get that same sort of shape, but I'd be to the left 2. Okay, so that's kind of just, and again, when you go into homework, you'll do similar type things, but you've got a little bit better tools where you can just sort of drag things and redraw them than trying to do it by hand. So here now is just starting to get us into is we're given the function, we're given a new function, and now we've got to figure out what happened to it, right? So you could graph both of these, but let's go with the toolbox function and see if we can just talk our way through it. So we know square root of x looks something like that. What has been done to if we think of this as being the square root function that's just been transformed? What should we do first? Again, think of order of operations. When we have order of operations, what do we do first? Inside the parentheses. So we come inside what's happening. Subtracting 1. So it's going to move to the right one. Good. So that's sort of an intermediate. We're not quite done yet, but it would kind of go like this. And then what do we do after that? we would move it up 3. So we take 1, 2, 3, and I'll do that in blue as sort of the final with that kind of shape. So over 1, up 3. And if you just sort of think of following order of operations, you'll always be right. Sometimes you'll get the same answer, not quite following the order of operation. We could have moved it up 3 and then over 1. That still would have worked. We'd end up at the same place. But I know you'll always be safe if you follow order of operations.
So the red line is what's been given, what x squared is.
Yes.
The green line starts at 1 because we're doing the opposite inside the function. The
Yes.
1, and
Oops.
then the blue is the going up positive.
Yeah, let me get my color coding in sync. No, you're good. So what I did is this part is the green.
Okay, I see that positive 1, you just moved it over 1.
Yes.
Okay, and
Then
then, but if it's the opposite, would it be negative 3?
Remember, outside it's exactly what you think.
Oh, outside
So that's,
is exactly
yeah.
what you think, inside it's opposite.
Yeah, and this is the hardest part of it. It kind of switches back. It would be nice if it was just all consistent, but it's not. Inside, everything's backwards. Outside, everything is, you get what you see is what you get.
Okay.
So you got to remember to kind of get your thinking switched. Okay. But some processes are that way too, you know. So far so good? Kind of making sense. Okay. So now what they want us to think, it's not really clear what they're saying, but if so this is a new function. If we started with some function, we'll go with g of x, was x squared, right? Because that's what this is. This looks like an x squared. What did we do to x squared to get this new function?
Moved it down 3.
We moved it down 3, so that would be outside, right?
So it'd be like
And then
x
minus
minus 1.
And we moved it to the right. Good. So moving it to the right is negative 1. And then this is squared. So this is happening in, actually, this is function notation. And so what the formula starts to look like, yes, is x minus 1 squared minus 3 on the outside. With just function notation f, I guess this is actually, this is what we did to g. So g, we subtracted 1 inside, subtracted 3 on the outside, and that would give us our new function. And again, what g started with was just the x squared function. And again, we could kind of just do it with a quadratic just by following that vertex. Everything will follow along with it. Is it kind of making a little more sense? There? Okay. An absolute value. So what does the absolute value of x, what does that graph look like?
It's like a v.
It's like a V. Actually, I think I can draw better straight lines. So I'll go from here. Come on. Yeah, close enough. And then it'll go from here to sort of like that. So that's our first graph. What will the new graph look like?
Move it to the right 2,
Move it to the right 2. So 1, 2.
up 4.
And then up 4, 1, 2, 3, 4. So again, you just sort of follow the vertex, and then everything else follows suit from there. You still have that V shape. Okay. And again, that's the functions they give us. Find a point to focus on. And
So if it's a graph that doesn't have like a vertex, it's just like one of those squiggly line looking ones, do you just pick a point and use that to kind
yeah,
of follow?
and you'll see like when I had that sort of the W-shaped one, I chose a couple points, moved them over, and then I tried to make it look like it was. Sometimes in here they'll actually give you that, and all you have to do is move the whole graph. I think so, but yes, take a point And then just make sure all the other points move along with it. Good. Okay, reflections. Again, I left in all the wordiness of it, but if we put a negative on the outside of a function, remember that's going to change the y values. So we get our y value, and then we make it the opposite is the way to think of it. So if this is the x-axis, any positive y is now going to become a negative y. Any negative y is going to become a positive y. Okay, so because you multiply by a negative, that's what happens. Negative times a negative is positive. Negative times a positive is negative. I get myself confused here. But it's going to flip over the x-axis. So they call that a vertical reflection. If you put the negative inside the function, you're changing the x value. So a positive x becomes negative, a negative x becomes positive. It's a reflection over the y-axis. Horizontal reflection. So that's when it's inside the function. Okay. And again, we're either taking -1 times all of the outputs, and that does a reflection over the x, or if we're putting it in first, we're multiplying all the inputs by a negative, and that does a reflection over the y. Sometimes we can't tell the difference, right? If you've got a x squared, you do a reflection over the y and you get the same thing because it's already symmetric. Okay. Okay, so now we're given this this graph that we're asked to reflect vertically and horizontally. So we'll do this one. So first we'll draw this graph. Remember, absolute value with -1. Where's the vertex of this going to be?
0, 0.
Well, if it was absolute value of x, it'd be at 0, 0, right? So they've actually,
Goes down 1.
yeah, over 1 to the right, to the positive direction. So yeah, so that was the first thing, is it's going to be here. If I can get that, something like that is going to be our V shape. And then if we want to reflect it vertically means over the x-axis, right? What's going to happen? All the positive y's become negative y's. All the positive y's become negative y's. So it'll be like that. And the reason they had it flip off of 0, 0 is because if they didn't, when you reflect it horizontally, you wouldn't be able to see the difference, right? Let me just redraw it. So we're here. Something like that. And now when we reflect all these, let's go here. So think about what point doesn't move? The one on the y-axis, right? It's not going to move because it's already at 0. But all of these here, so this part is going to come over here. This part will go there. This part that was negative x's is going to become positive x's and go there. So it reflected over the y-axis. Okay. And again, you could try that with decimals, and you would see, you know, you can put this in as the absolute value of x minus 1. In fact, so we're doing okay on time, so let's give that a try. Let's keep these, and let's go decimals. So here I could change this to, see, where's the absolute? I think this one, absolute value of x, let me do this, x, what was it, x minus 1. right? So there's that. And now the vertical shift would be a -1, the one in front. So if I change this to -1, notice that's what we have. I'll put it back. And if inside I change this to -1, this kind of goes through a transformation process, but watch, I'm almost there. There we go. Switched off the colors, but it's on the other side. So you can kind of, and I encourage you to kind of go back and forth and play with visually seeing it with your calculator of what's happening. That gives you a deeper understanding. Okay, so we got that. How does that look with the table? So A, we're going to recreate a new function. Where is the negative going to go on? Is it going to go on the X or on the Y? The Y. So X, we'll make up a new table. This will be G of X. So we have -2, 0, 2, 4. And all the y's are going to change their sign. So this will be -5, -10, -15, and -20. So that's the A. For the B, where does the negative go? It goes on all the x's. And this is the one that's not backwards. You put a negative on each of the x's. So we have -2, that's going to become a +2. 0 doesn't change. +2 becomes -2, and +4 becomes -4. So the x's change. Oops, this should be h of x. The y's don't. And if you were to graph those points, you would see that this is a reflection over the y-axis, and that this one, when you change the y values, is a reflection over the x-axis. So there's kind of that opposite. Change the y's, you're going to reflect over the x. Change the x's, you will reflect over the y. Okay, and again, we could do the same thing here with a x squared. The thing is, when you reflect it over the y, will you see anything different? If I reflect that over the y-axis, it looks exactly the same. We sort of looked at that. If I reflect it over the x-axis, I see a difference. So this one does look different, right? This is negative f of x, so that's a reflection over the, you're changing the y's, reflection over the x-axis. But if you do a reflection over the y-axis, which is this one, it looks exactly the same. It's just that this was the positive part, this was the negative part, so they switch places, but since it's symmetric, you don't see a difference.
So if the negative is next to the f, it's in the x-axis?
Yes.
Okay. And the opposite is the y-axis?
Yes. So again, kind of an opposite. That's an x-axis flip. This is a y-axis flip, reflection. So far, so good. And how many of you are into art? They actually have a whole. I've always wanted to go to the south of Spain, where the Moors, they have the Moorish culture. They're Arabs that came up, took over part of Spain, but they have these tiles. Their tiles actually have the algebra of all these types of translations. If you look at them, the tile patterns are reflections. It's just supposed to be really. I've seen some pictures. It's beautiful.
Crazy symmetry.
Yes, I just like to go see it in person. Actually, these are 100-year-old, some maybe even 1,000-year-old tiles of about the 1200s, 1300s. But south of Spain, someday I'll get there. But there's a whole algebra, and I've seen a book, at least a chapter, a book was written on the algebra of those tiles, artistic. Okay, we talked about these, so stretches and compressions. So if we multiply on the outside, again, outside, it will happen exactly as we think. So if we multiply by a number bigger than 1, we get bigger, we get a stretch. If we multiply by a number smaller than 1, a decimal, that's like dividing, right? We get a compression that happens vertically. If we're doing it inside, it's going to be a horizontal, and it's always the opposite. So multiply by a number bigger than 1, it's actually a compression. Multiply by a number between 0 and 1, we get a horizontal stretch. Okay. So again, for vertical, if it's greater than 1, we get a stretch, a vertical stretch. If it's between 0 and 1, then we get a compression. Again, thinking of that as a fraction, a decimal. And then if a is negative, basically the same thing will happen, but we get a free reflection, because that negative has a separate effect. Just the negative alone will reflect it. What does it reflect over the x or the y? It reflects it over the x, right? Because we're changing the y, so it's an x-axis reflection. And so they show that here. Yeah, if we multiply, we're stretching it upwards. If we multiply by a decimal, say like 0.5, it's going to compress it or push it down. And then if we were to throw in have it be a negative number, we'd see the same effect, but we'd see it kind of down here of reflection as well. I like to think of them as two separate things, but you can put them together. So again, we could do that here. If create a table for the function 3/4 f of x. What do? We just multiply each of these numbers by 3/4. And notice they chose numbers that are all divisible by 4, so that makes it nice. And we see 2, 4, 6, 8. 3/4 is a fraction. It's less than 1. We should see these numbers get smaller. 12 divided by 4 is 3. 3 times 3 is 9. So that's smaller, right? That's a compression. 16 divided by 4 is 4. 4 times 3 is 12. That number's smaller. 20 divided by 4 is 5. 5 times 3 is 15. That got smaller. And 0, that stays at 0. Okay, so we can kind of see it from multiple perspectives, and that's what the homework will also help you do, is see it as a table, see it as a graph, see it as a function, and just kind of get this feel. But just remember, there's only two things that you can either be inside the function or outside the function. There's only two of those. Outside the function always affects the y values up and down. Inside the function always affects the placement of the x. Outside the function is what you see is what you get. Inside the function is like looking in the mirror. It's being in the looking glass. It's always opposite. And then that's good. So again, we could do it with these. Again, there's no vertex, but it's just shift the whole graph. Stretch it by 3. These are going to be harder to draw, but stretch it by 3, down by 2. So I think we could have multiple transformations, again, where you have translations, you've got a stretch or a compression out here, you've got a reflection. And what I'm going to say is, when they give you something like this, it's probably best to go ahead and graph these. Let me show you. Did I ever show you how to do an absolute value graph on the TI-84 calculator? I haven't. Would you like to see that? Because that's, since I got it here, so let me pull up my TI-84. Where am I? Got to go here. And well, it's -2 absolute value. Okay. Yeah, I knew it would. So I go into here. Do it with that one. So let me get rid of these. So what I'll do is I'll first grab the absolute value of x. To get the absolute value, you go to the math key. And then you have to go over 1 to number. It's a number function. ABS is absolute value. So you hit enter, and notice mine gives me the absolute value. If you got an older version, it might say ABS with parentheses. But I'm just going to graph first just the absolute value function. And then I'm going to go zoom number 6, which is a standard, gives me the standard window. And that's the absolute value we've been talking about, right? So now I want to see what happens if I take that same function, but I multiply it by -2 on the outside, math over 1 absolute value, right? And what did we have? It was x minus 4? Does anyone remember? I forgot. Let's see, I think it was in this one. X minus 4, and then plus 3 on the outside, okay. So then we could put in x, oops, oh, I gotta be in there, x subtract 4, and then I could put plus 3. Now you could also graph these individually. In fact, why don't I do that? I won't put the plus 3 yet. So what's going to happen here? This minus 4 is going to move it which way? To the right 4. This negative is going to reflect it over the x-axis, and the 2 is going to stretch it vertically, right?
But it would be like over the x-axis, but it's also like down 2, right?
Yes, yes. So let's look at that. And so it got moved over 4. It's hard to tell that it's stretched, but you can see it's a little bit steeper than up here. And then we come back here, we've got a plus 3 on the outside. And what's that going to do? That will move it up 3. And remember, last time it was down here, so it's been moved up 3.
What was the button you hit on the calculator to get that absolute? You were writing it out?
Go to math. So once you're in here, you hit the math key first, and then you go over to number functions, and it's number 1 ABS.
Okay. But when you were typing it in, you were typing in -2, and then you had the...
Oh, yeah. So I went, let's clear. So I did -2 first, and then I go to math, number, ABS. Every single time you want, yeah. So it's kind of like...
So you're going to do that after the 2, too?
Right. Yeah, because that's where I want the absolute value, because I wanted the -2 in front of the absolute value.
Okay.
And That makes sense. So, yeah, and if they wanted me to do it again, we don't do too much with it, but that at least you can now use your graphing calculator. You can also do it with decimals. Decimals just put in the absolute value bars. But I think it's important to practice a little bit with that. Let me just see. We got a few more. We might skip over some. This when they give these PowerPoints, they show us multiple ones. So I guess part of it is this is a transformation. What did they do if we started with absolute value of x? Right, absolute value of x would have been this one here. So what happened to get this to happen?
It's up 1/2.
So up 1. So absolute values, we're going to add 1 on the outside. What are we going to do on the inside? Plus 2. Because we're moving it in the negative direction. It's always, yeah, those are the trickiest ones. I'll miss them. Yeah.
So x, because, where are you looking at first on this formula? Are you looking at f of x equals absolute of x? And then you
Yeah. So I'm starting with the absolute value of x. And so what do I do to this formula? Well, I have to, if I add 2, that moves it to the left 2. So I get up there. And then this plus 1 on the outside moves it up there. And I don't think it's been stretched or anything. Sometimes it's hard to tell, but we'll just assume it hasn't been stretched.
It looks like more like outer.
Yeah, you're right. It's because usually it's 1 to 1. It would go like here, and so it's been stretched out to 2. It's probably been multiplied by 2 or a half. Actually, it's maybe a compression. Maybe that. It's hard to tell because it now takes 2. You have to go over 2, so the slope is 1/2. Rise of 1, run of 2. Kind of see it that way. But again, mostly to see what happened to the vertex. And then, so from the graph, kind of be able to figure out what the transformation is. And they show you multiple things. So if we start with this, again, to do this is really a 3-step. We did all of this. Actually, I think we may have had different numbers on the ones we did, but let's see, what did they start? They started inside. They subtracted 3, so they moved it to the right 3. They did the vertical stretch. That gave them the green one, and then they finally moved it up 4. So kind of following order of operations. You can draw that new one. But a lot of times if you can just graph them on the same, use your graphing tools, they'll help you see what's going on without too much. Okay. We've already talked about the absolute value equations or inequalities. Absolute value equations are basically the same, except so you always, with absolute value, you get a plus or a minus. Solving an absolute value equation. So again, this is sort of, we did x minus 1 minus 3. You could do it by graphing. You're finding where it crosses the x-axis, or you could solve it by hand, wherever this is equal to 0. And again, we add 3 to both sides. X minus 1 equals 3. Now it's at this point that we've got the absolute value isolated. What do we do with it? We get x minus 1 equals 3, or x minus 1 equals negative 3. Okay, because if we had a negative 3 inside, we'd get that. And notice we didn't have to, because it's equals, we don't have to worry about flipping the symbol or anything. So we add 1 to both sides. X equals 4. We add 1 to both sides. X equals negative 2. And so what that's telling us is that whatever this graph looks like, there's going to be crossing the x-axis there, 1, 2, 3, 4, and there. Notice this is we moved this way and then down 3. That would be our vertex. So that makes about sense. If you would have graphed it, you would have seen something like this. So you can either solve it with the algebra, sort of solve it by working with the function itself like we did here, or you could just graph it, and then you could graphically see, well, it's equal to 0, where y is 0 is where it's crossing the x-axis. Okay, so both ways work. Yeah, so that's, we can use this concept of transformations to kind of see what the, get a vision of a graph without actually having to graph it.
And then you got that where the vortex is, that bottom one, because a -3 stays -3 because it's outside.
Correct.
X minus 1 becomes X plus 1, which is just the over.
Yes, exactly. So the vertex went from 0, 0 to 1, -3. Exactly. And so we can kind of visualize things. So I'm giving away all my secrets. You think, oh, how does he know what the graph looks like? All of this stuff. Okay. We'll maybe talk about, well, even or odd functions. You can take a look at this a little on your own. We're close enough. If you have some questions on it, we'll talk about it, but it's about symmetries. So on Monday, it's like 5 or 10 minutes. We'll take a look at it and then get into the homework and do the test then. So we try to squeeze it in now, we wouldn't know it. Awesome. Thank you.